Alright folks, so I guess some people are still asking about the MoonHop questions, so I thought I can solve that. Let you know about like the little tips in there. So first of all, the first thing is parsing the question, right? We agreed, we read the question, we parse out the information. So an engineering company has designed a lunar vehicle, right here, to explore the surface of the moon in big sweeping hops. So we're expecting that, this is going to be a projectile question. To accomplish this, they outfitted the lunar vehicle with two boosters, one vertical and one horizontal. The vertical booster is designed to launch the lunar vehicle with some initial speed of 4.86 meters per second in opposition to the moon's gravity, whose magnitude is given. And the horizontal booster is designed to make the lunar vehicle hop a horizontal distance of 60 meters if the vertical booster works as designed. Okay? Now what happens during the mission is that the vertical booster works as designed on every attempt, up and down, but the horizontal booster only worked on some attempts and completely failed on other attempts. So we're expecting on the failed attempt that the horizontal booster doesn't work, so the vertical is just gonna go up and down. And then on the trials that the horizontal booster works in addition to the vertical booster, we're expecting it to be a 2D kinematic problem like this, okay? So let's see what the questions are. So first of all, it's asking for the attempts where the HB fails, the horizontal booster fails, so we're just going up and down. Let's calculate these four things. The maximum height, the time it takes to get to the maximum height, the total flight time, so up and down, and the final velocity when it lands back on the surface of the moon. So let's start with the maximum height. To set up the maximum height, we have to think about the problem. First of all, like we agreed, we draw the problem. So I have a lunar vehicle that starts out in its initial position. It's on the surface of the moon. So this is the surface of the moon right here. And here's the lunar vehicle. Looks like this. And the vertical booster somehow gives it a boost with some initial velocity that is given to us as 4.86 meters per second. And this is said to be in the opposition to the gravity of the moon, which would be the acceleration of 1.62 meters per second squared. Of course, this is opposite to this, so depending on which direction we end up choosing as the positive, one of these is going to be negative. And then for the first part, calculate the maximum height. So the maximum height is this final position in which the vehicle stops moving up and switches its velocity to be pointing down. So that's where v is equal to 0. Vy, of course, right? We're talking about y pieces here. I could have left the y subscript off because the x part is not working in this because of the horizontal boosters failed. However, we'll just keep the y label to remind ourselves. Okay? So parts A and B are both talking about this situation in which the initial position is on the surface of the moon and the final position is when it stops in midair before it starts coming back down. We know V naught, we know AY, we don't know Y, and we don't know the time, but we know the final velocity. We know that, but we don't know the time. Okay, to reach the maximum height. So if I know these three and I want to calculate the maximum height, I think I would use this equation. So for part A, I think I would use the equation y equals v squared minus v naught squared over 2a. I'm going to choose up to be the positive direction, so that means the acceleration is going to be negative. Okay, Vy is 0 because it stops, minus V naught y is given to us, 4.86 meters per second, and this is all squared, divided by twice the acceleration, so that means twice 1.62 meter per second squared. And if you work that out, you'll find that the height is equal to something like 7.3 meters. Okay, that's the maximum height. Now for part B, we're asking about the time it takes for the lunar vehicle to get to the maximum height. So we're still talking about the same setup of the problem, where this is the initial spot where it's on the surface of the moon, and the final spot is where it hangs in the air before it comes back down. So I know the same things again. I added y here, so I can actually use any equation I want that has t in it, and that will give me the proper solution for t. So I could start by using this equation. T is equal to, to find t, y is equal to v naught y t plus half a y t squared. Obviously, if I sub in all the numbers I have, 7.3 meters, 4.86 meter per second for v naught y times t plus half the gravity of the moon t squared. This is a quadratic equation that I set up that will give me two values of t. I imagine one of them is going to be negative and one is going to be positive, and we're going to end up taking the positive value. Or I could use this equation that doesn't have y, which is the thing that we got in part A. So uses the things that we were given in the problem, which I like better. So for that, Vy is equal to V naught y plus Ayt. V naught y we know is 4.86 meters per second, and Ay is 1.62 meter per second squared times t, and of course Vy is 0. From this, I can find the time, which will be minus 4.86 meter per second over minus 1.62 meter per second squared, and lo and behold, that gives me 3 seconds. Okay? Just move this. Subtracted 4.86 from both sides, and then I divided both sides by minus 1.62. So I got t to be 3 seconds. And then part C is asking about the total flight time. Right? So the total flight time, as we've seen from lectures, this is it's a totally symmetric problem, right? So now, instead of talking about the initial and the final as being, the initial being the surface of the moon and the final being where it stops in midair, the initial is now a surface of the moon, and the final when it comes back to the surface of the moon, right? So I could solve that problem in two parts. I could solve the part that I already solved, which now I have all the information for, and then the second part I could start from the initial being now in midair, so this will be my initial, and then now I'm going back down, and the final is going to be when I touch back the surface of the moon. Okay, so we could do this problem, but we already know from class that this problem is totally symmetric to this problem. In other words, V naught now is going to be the final V from the other part, and the final is going to be the initial from the other part, and the time is going to be equal. The time going up is the same as the time going down because I'm returning back to the same exact height that I started from. So in this case, I can straightforwardly say that the total flight time is equal to six seconds. You got it. Right? 3 seconds on the way up and 3 seconds on the way down. Okay? Fantastic. And then we've just said, as we were explaining this bit, that the final velocity, just like we remember from class, from the coin example, when you flip a coin, it goes up and comes back down with the same velocity, or with the example where you throw a stone off a cliff. In both examples, we've seen that the symmetry of the problem tells me that the final velocity is going to be the same as the velocity it was launched with, except in the opposite direction. So in this case, it's going to be the same magnitude, 4.86 meters per second, but now it's going to be in the opposite direction. So the correct answer is minus 4.86 meters per second. Now we've just solved C and D by resorting to the symmetry of the problem. But what if I had wanted to solve these parts without resorting to the symmetry of the problem, without knowing anything about the time it takes to the maximum height? Can I find the total flight time and the final velocity when it lands? And I think the answer is yes. And the way I would do that is by just considering the situation where the initial is when it leaves the surface of the moon, the lunar vehicle, and it leaves at 4.86 meters per second. It goes up and comes back down in the same spot. There is no x displacement at all, but I'm just going to draw it next to it. Then it's going to come back down and touch surface of the moon, and it's going to come back down with some velocity vy, which I don't know. Now in this case, the kinematic variables are v naught y, which I know, ay, which I also know. Now I don't know vy, which I'm looking for. I'm also looking for the total time. And the key point here is that I know that it comes back down to the surface of the moon, so I know what y is. So if I wanted to find vy, for example, which is part D, I would use the equation vy squared is equal to v naught y squared plus 2ay. I know y is 0, so this goes away. So vy squared is equal to 4.86 meter per second plus or minus. Vy is equal to plus or minus 4.86 meters per second. Right? Of course, I'm going to choose the minus in this case. These are the directions. And of course, I'm going to choose the minus in this case because it doesn't make sense for Vy, when it comes back to land on the surface of the moon, that the velocity would be pointing up. So in fact, the negative makes physical sense. Okay? And then, now that I know the velocity when it comes back down, I can use that to calculate the flight time, because I know that v final is equal to v initial plus the acceleration times time. I know that this is, I just calculated this to be minus 4.86. I've calculated this to be 4.86. Sorry, that was given. And then this one is minus 1.62 meter per second squared times t, which means that t is equal to twice minus 4.86 over 1.62, which is going to be equal to 6 seconds. Okay, which confirms what we found using the symmetry. The next part of the problem is going to be a different situation in which now the horizontal booster succeeds. So in this case, my lunar vehicle, instead of just going up and down, it's going to take this projectile motion, the classical shape that we know. So what do we know about this? Here's the question head. Question head is asking what is the maximum height. Again, we're still asking about the maximum height, the total flight time, the final velocity when it lands back on the surface of the moon, and then we're going to plot some things. So first of all, what is the maximum height? Of course, like we said, if we believe in our hearts that the x part and the y part of the kinematics are separate, then the fact that the h booster succeeded does not change anything about the y piece of the kinematics, which means that right away I can tell that the height, the maximum height, was also the same as the maximum height when the h booster failed. Same thing applies for the total flight time. And now for the final velocity piece, I'm going to have two pieces to that. First of all, I'm going to have the final velocity is going to have some component in the x direction and some component in the y direction, and this one is known. We've just calculated that to be minus 4.86 meter per second. So all I have to do now is just calculate the x piece of the velocity. How do I calculate the x piece? Let's write the x kinematic variables. I know that v naught x I don't know. Vx also don't know. The acceleration in the x direction I know because there is none, because it's equal to 0. And the total flight time is something that is common between the x and the y, and I know that that's 6 seconds. I've calculated that, and I know that it hops, as per the question head, a horizontal distance of 60 meters. This is the horizontal hop. Okay, so now that I know that ax is equal to 0, t is equal to 6, and x is equal to 60, I can find out v naught x and vx, because of course because there is no acceleration, I know that these two are equal. The one equation that's left to me to use is the one where it says that x is equal to v naught x times t plus half ax t squared. So if I sub in with 60 meters is equal to v naught x is what I want to know, t I know is 6 seconds, and the acceleration is 0. Then from that I know that v naught x is equal to 10 meters per second. So I know that v naught x is equal to 10 meters per second is the same as vx, but I also know that vy is minus 4.86 meters per second. So if I use these two pieces of information, I know that vx is equal to 10, and vy is minus 4.86. Then I can get the magnitude of v, which is, by the Pythagorean theorem, 10 squared plus minus 4.86 squared. And the angle, of course, can be found by the arctan opposite over adjacent, opposite of theta, adjacent to theta, minus 4.86 over 10. So now I know the magnitude and the direction of the final velocity, which is the velocity of the vehicle when it lands back on the surface of the moon. So knowing these pieces of information, let's go and graph these things. So for the graphs, we're going to be plotting 4 things, and for each one of these graphs we're going to plot the failed attempt and the successful attempt of HB. So the things that we're going to be plotting are position of x versus time, position of y versus time, velocity of x versus time, and velocity of y versus time. So first let's start with the x position versus time. And for the fail attempt, that's pretty straightforward, because the lunar vehicle just moves up and down. It doesn't move in x at all. So x is going to be equal to 0 the whole time. So from t equal to 0 all the way to t equals 6 seconds. As for the velocity in x, it's also going to be equal to 0 for the fail attempt all the way to t equals 6 seconds. Okay? On the other hand, when HB is successful, the position of x we know is going to change from x equals 0 at t equals 0. We know that it's going to go with constant velocity, right? We know that there's no acceleration in x, so v naught x is equal to vx is equal to 10 meters per second. So that means that at 60 meters, this is how the position of x is going to change with time. And of course, this is the slope that is that constant velocity, 10 meters per second, right? So, so you know that v naught x and vx is going to be equal to 10 meters per second all the time. All the instantaneous velocity is the same throughout. So it's just constant at 10 meters per second. As for the y position, actually let's leave the y position for a second. Let's look at the velocity in the y direction. So when it fails, when the horizontal fails or the horizontal succeeds, we expect these two graphs to be exactly the same, right? We know that in our hearts we separate the x part and the y part, right? So in the y part, whether the x succeeds or fails is not going to make a difference. So that's why these two curves are going to be the same. The dashed and the straight line are going to be the same. In the x part, the dashed and the solid are not the same, because it depends on whether the horizontal booster succeeded or failed. In the y part, the horizontal booster succeeded or failed does not factor in the graph. So the dashed and the solid are going to be the same. Let's start with Vy. We know that at t equals 0, Vy was something like 4.86 meters per second, positive. And we know that the only thing that was acting was the acceleration of the gravity of the moon, which we know is negative. And in v versus t, the acceleration is the slope of the line. So we know there is going to be a straight line that has the slope minus 1.62 meters per second squared. And we know that at 3 seconds, the velocity is equal to 0. And we know that at 6 seconds, the velocity is going to be equal to the negative of this value, negative 4.86 meters per second. And we know this is of course going to be a straight line, and we know that the dashed and the solid line are going to be right on top of each other, right? The slope here of course is minus 1.62 meters per second squared. Now if I'm looking at the y position, I know that the slope of the y versus t is going to be equal to the instantaneous velocity Vy. In other words, at t equals 1 second, the slope of the curve is going to be equal to whatever the value is of Vy at 1 second. 1 second, I know what the value of y. So at 1 second, the slope of the curve is going to be equal here. So look at this. The velocity of y is decreasing. So that means the slope of the y position versus time is decreasing. It starts high and starts decreasing until the velocity reaches 0 at 3 seconds. That means that at 3 seconds, the slope of this curve is going to be 0, which means that it's going to be horizontal, like this. It's going to be flat. So the slope is going to be the highest at the beginning. It's going to keep slowing down until it reaches 0, and then it's going to start increasing again negatively increasing. So the slope is positive this way, and then goes all the way to 0, and then goes negative, increasingly negative. So now it's gonna look like a parabola like this. This is 6 seconds. And we know, of course, that the dashed is the same as the solid, because it doesn't matter whether the HB fails or succeeds. And this concludes the Moonhopper question. If you have any questions, please email me. Have a good one.